My name is Jonah, and I'm going to be talking about stars today, both how they're born, how they die, and we'll take a couple tangents along the way showing just how big some of these stars can be. But before I get started, I might just introduce myself. So I am a PhD student at Mount Stromlo Observatory, which is a part of the Australian National University here in Canberra. My PhD project is to essentially build a telescope in Mount Stromlo's car park. And it's designed to be about 30 to 40 meters big. So this is a huge telescope, but it's actually not going to be building like a mirror that's 30 to 40 meters big, because that would be absolutely insane to build. Instead, I'm using a process called interferometry, which another PhD student, Adam Rains, talked about a couple of weeks ago. So if you scroll up the Facebook feed, you might be able to find that from a couple of weeks ago. And he talks a lot more into what interferometry is. It's essentially using a bunch of really small telescopes to pretend they're one big one. But I'm not going to be talking about today, but that's what I do on a day-to-day basis. I also love looking at exoplanets. So these are planets that go around stars other than the sun. They're quite mysterious. In fact, it was only about 30 years ago that the very first one was found. So it's a rather new field, very exciting. And so it's another one of my passions to look at these exoplanets and maybe even discover whether or not there might be alien life living on these planets. But that's enough about me. Let's get into the meat of the topic for today, and that is stars. So when I say think of a star, some of you might think of this kind of pointy shape, kind of like what's on the screen here. And I mean, we even call them stars. They're star-shaped. But in reality, stars don't look anything like this. They're actually quite perfect spheres that are full of, that are really hot, really big, and are actually made of something called plasma. You might have learnt in school about the 3 states of matter. You've got solids, which are something like hard that you can hit. You've got liquids like water, and then you've got gases like the air around us. But there's actually a 4th state of matter, and that is plasma. And this is what happens when you heat a gas really like extremely to extremely hot levels. And then this gas kind of gets electrically charged and behaves quite strangely, and that's exactly what stars are made of. But then I suppose you might ask the question, if stars are perfect spheres, and because they're so far away in our sky they would look like dots, why do we have this kind of star-shaped shape? And it's actually quite interesting to learn why. And it has to do with the fact that telescopes and even our eyes aren't perfect. So on the screen here, we have a picture taken by the Hubble Space Telescope. This is one of the biggest space telescopes we have in our sky, and it's taken lots of beautiful images. So most kind of stunning images of space that you can think of are generally taken by the Hubble. And as you can see here, they're not perfect spheres, even on this Hubble image, but they've got these kind of points. And these points are what kind of looks like a bit of a star shape. And I suppose you might be asking, why does it look like that? And that's because on the other image we've got here, which is kind of the Hubble mirror, it's holding up a secondary mirror kind of in front of it. And that's being supported by 4 little kind of metal rods. And when the light from the star goes past these metal rods, it kind of creates some strange patterns. And that's exactly what gives these kind of circles, these kind of long points. And the same thing happens with our eyes. Our eyes aren't perfectly smooth. They've actually got a few little imperfections in them. And so when the light goes past them, it kind of creates these little star shapes. So when you go out on a dark night and you look up at stars and you'll see them twinkling, you might see these stars kind of got odd shapes, and they'll look like kind of little stars. And it's exactly, it's because of your eyes rather than the stars that they kind of look star-shaped. But we'll finish with that little tangent, and we'll start heading on into essentially how are stars born? How are they formed? So here's a picture of a well-known constellation. It's the constellation of Orion, and we can see this in Australia quite often during most of the year. And you also might know of a part of Orion called the saucepan, which is kind of in the middle here. You've got 3 stars which kind of form the base, and then you've got another kind of group of stars that form the handle. And what we're going to do is we're going to zoom in on this handle here. You can see this kind of pink smudge. And so when I zoom in further with the Hubble, you kind of see this huge nebulae. And it's really quite beautiful. It's kind of all this gas and dust kind of all spread out over a huge distance. Like, we're talking absolutely enormous. So parts of this kind of gas and dust cloud start forming other little clumps. So everything has gravity. That is this force that kind of pulls things that contain stuff together. So it's what's keeping me on the ground here, and when you jump up, it pulls you back down. So parts of dust and gas in this cloud also have gravity. And some parts might be a little more clumpy than others. And so they will kind of start drawing more gas and dust together. And then that little bit of gas and dust will start drawing more and more together. And eventually a lot of gas and dust are kind of clumping together until you get this nice little ball. And eventually there will be so much gas and dust, so much matter in one small little spot, that it will start to try and ignite itself. It will start to kind of, like a car engine, kind of turn on. It will kind of like rev up and see if it's going to ignite or not. And I've got a little movie here that kind of shows how this works. So we kind of zoom into a little gas cloud, and what's happening is the gas and dust is all kind of falling on each other, and eventually you'll see some little dots that are kind of flying around. And these little dots are stars. They've managed to turn themselves on and essentially kind of catch on fire, though it's not quite fire. And once they kind of turn on, they start glowing really red hot, and will kind of keep taking in gas and dust. And so this is essentially how stars are formed. They kind of pile on gas and dust and essentially ignite, and that's what forms this kind of big glowing hot ball of plasma in our skies. One second. Of course, though, sometimes, even though like, gas and dust is piling on, sometimes it just won't be enough. Sometimes you won't get enough gas and dust for it to turn on. It will be kind of like a car with kind of a broken engine. It will kind of rev up, but it won't quite turn on. And these are kind of failed stars. They're stars that didn't quite make it. And we call them brown dwarfs. They kind of look a bit like gas giants, because they're full of gas and dust, but they're not kind of on fire or like kind of undergoing nuclear fusion, which you will learn about later on in school. So we think that some brown dwarfs might actually be really large gas giants, so really large planets full of gas that might be around other stars as well. So brown dwarfs are essentially stars that, well, they're not actually stars, but they're balls of gas and dust that didn't quite become stars. But then you've got the ones that did, and we call them main sequence stars. So our sun is exactly a main sequence star. It's kind of in its middle age. It's just kind of going about doing its own thing. The remaining gas and dust, once the star has ignited, will kind of form in a ring around the star due to it, the star's normally spinning. And so you've got all this gas and dust going around in a ring around this kind of big ball of gas. And that gas and dust will eventually form planets around the star. So another PhD student, Eloise, gave a talk on how planets are formed. And so if you want to learn more about that, I would recommend checking out her talk. I won't be going into much about that. But these planets are made of the same stuff that the star was formed out of. And of course, we, like humans and animals and birds and fish, we're all formed of stuff that the Earth was formed of. So essentially, you can say that we are made of stardust. We are made of stars, which is kind of cool to think about. But stars aren't exactly peaceful places. I mean, they're huge balls of plasma, huge, really hot, glowing objects. And you can kind of think of them like a bunch of nuclear bombs going off. But how many nuclear bombs, I hear you ask? Well, it would be about 100 trillion nuclear bombs. And at least that's what it's like for our sun. Our sun is essentially the equivalent of 100 trillion nuclear bombs going off every second. So that's a lot of energy, and it would blow your socks off. But the sun is, thankfully for us here on Earth, the sun is far enough away that we don't get all 100 trillion nuclear bombs exactly falling on us every second. Instead, we get a fraction of that. And so we are able just to have a nice warm summer's day rather than nuclear bombs going off around us all the time. But stars don't stay in their main sequence life forever. Eventually, they'll start running out of that gas that they use to kind of ignite and turn on. And when they start running out, they'll tend to puff up a bit. They'll kind of expand. And this is what we call a red giant. And our sun will do this in about 5 billion years. So you or me won't be around then, but people perhaps 5 billion years in the future may have to deal with the fact that the sun becomes a red giant. And when it does this, it will expand past Mercury, past Venus, and it might even swallow up Earth. So these stars get quite large. But yeah, this is only in 5 billion years, so don't have to mark your calendar for this one. Once it's kind of passed, it's kind of swelled up, eventually it won't be able to hold on to all that material anymore, and so it will just kind of let it go. It will just let lots of the material it was holding all kind of just drift away. And what you're left with is a white dwarf. So in the image here, you can see this is the Southern Ring Nebula, which if you've got a really good telescope, you might be able to see at night. But you've got this little white dwarf here, this kind of little star. These are a lot smaller than their kind of main sequence, their normal star counterparts. But you can also notice this like nice kind of ring of gas and dust around it. And this is the material that used to be kind of on the star, kind of igniting and bubbling away, but now it's just kind of floated off. And it can create some really pretty shapes. So here we've got the spiral planetary nebula, the gas and dust that kind of floats away from these white dwarfs we call planetary nebula. They're not actually related to planets. Unfortunately, the naming conventions at the time were a bit murky. So planetary nebula don't have to do with planets. They actually have to do with stars that have kind of passed their expiry date and kind of just let all their gas and dust kind of just float away. But they create lots of nice little patterns and colors. And this is because this gas and dust gets hit by energy from the little white dwarf, and it kind of shocks it, and it kind of creates these nice colors. And the Cat's Eye Nebula is another really nice, beautiful looking planetary nebula. You can see this beautiful red and violet colors. So this is not just taken with the Hubble telescope. We also use some observations with an X-ray telescope. So this is kind of really energetic particles that kind of are much more energetic than normal light. And so this is colored here in kind of purple. So this isn't if you looked at this with your eyes, you wouldn't see this exactly, but we use special telescopes that we're able to kind of look at even more energetic particles coming from these objects. I'll take a moment here just to remind everyone to feel free to ask any questions in the comments, and we'll get back to them at the end of the talk, but highly encourage them and I'll do my best to answer them. So that was kind of the normal life cycle for kind of relatively small stars. So our sun is fairly small, fairly typical-ish, but it gets much more exciting when you look at stars that are a lot bigger. So let's, for instance, take a blue supergiant. So these are stars that are around 50 to 100 times bigger than the sun. And they're not just bigger, but they're also hotter. So you might think when you've got like a candle and you've got a flame, you might see that it's blue in the middle, but kind of orange on the outside. So the orange kind of flame on the outside is generally a bit cooler than the really nice blue kind of flame in the middle. And that blue flame is a lot hotter. And that's why things that kind of glow blue are generally a lot hotter than things that glow red. And it's the same thing with stars. When we look at stars that are blue, they're a lot hotter than stars that are red. So for instance, we can see a blue star by going back to Orion and the saucepan, which you can see on most nights here in Australia. And if you look up in the top left corner, you can see this really bright blue star, and that's called Rigel. And it's one of the most bright stars that we know of. It's not the brightest in the sky because some stars are a lot closer. Rigel's actually a long, long way away, 900 light years away. Now, light years is kind of a funny unit. You might ask, why use a term such as light years? And what a light year is it's the distance that light takes to travel that travels in 1 year. So when we say something is 900 light years away, we mean that the light from the star or the planet or whatever has taken 900 years to reach us, which means we're looking at this star 900 years in the past. So when you go outside perhaps tonight and look up in the sky and look at Rigel, know that the light that's coming into your eyes came off of Rigel back when the Crusades were still going on. So astronomy is essentially time travel. You're looking back into the past. And some stars and some galaxies are so far away that you look past the dinosaurs and you're looking straight back to the origins of the universe. And that's what cosmologists do. They look at the furthest things possible to try and work out what life was like at the beginning of the universe. But even though Rigel is really, really far away, it's still really bright at night. And this is because it's 100,000 times brighter than the sun. But when a blue supergiant kind of starts running out of its gas, it also kind of puffs up like a red giant does, but it does it on another level. And we call these red supergiants. So these are absolutely massive stars. And again, if we look back at Rigel, we can actually see one of these supergiants. And if you look in the bottom right, you've got a star called Betelgeuse. And this is one of the biggest stars that we know of in our sky. And you can see it quite easily, again, looking at Rigel. And Betelgeuse is, absolutely massive. It's 1,000 times bigger than our sun. Now, I've been talking about it's bigger than this, and it's quite large, but it's kind of hard to get a sense of the scale of these things. So we're going to do a little bit of an experiment. So I'm going to imagine that the Earth is a golf ball, or in my case, here's a little stress ball, which is kind of painted like the Earth. So imagine that everything that you know, all of the Earth, all the life, all the planets, all the humans, birds, whatever, are all living on this little ball. And we're going to think about how big are stars in comparison to this little golf ball. So let's start with the planets. If the Earth was the size of a golf ball, then Jupiter, which is the biggest planet we have, would be about 23 centimeters, or about a beach ball, so something like this big. And you'd be able to fit about the same number of golf balls in this kind of beach ball as you could fit Earths inside Jupiter. Now we can continue going up the chain. So if you look in the far left, you can see Jupiter. So already we're getting huge. And here you see the sun, which is a star. It's quite big. And if the Earth was the size of a golf ball, then the sun would be the size of my room here, about 5 meters or so big. Now, how many balls or how many Earths do you think could fit inside the sun? Well, if the Earth was the size of a golf ball, it would be able to fit about as many golf balls as you could fit into a bus. That's a lot of golf balls. It's about 1 million Earths or 1 million golf balls you could fit inside a bus. Before I go on, I should also mention this big white star here called Sirius. Sirius is actually with the exception of the sun, which is during the daytime, Sirius is the brightest star you can see at night. And it's not because it's brighter than, say, Rigel, which is this really bright blue supergiant, but it's bright because it's also fairly close to us. It's not that far away. So let's continue on. Now we'll go into the red giants. So those were kind of main sequence stars. They're kind of middle-aged, not exactly that big or exciting. these are a lot bigger. So these are stars that have kind of started running out of their gas and sort of puffed up quite a bit. So if the Earth was the size of a golf ball, Aldebaran, which is this kind of really big red giant, would be the size of a football oval. So if you imagine kind of getting a golf ball, putting it in a football oval and kind of looking up, that would be the size of these red giants. And how many Earths do you think could fit inside Aldebaran? Well, you'd be able to fit the equivalent number of golf balls in not just one, but 2 pyramids of Giza. So imagine how many golf balls you could fit inside 2 pyramids of Giza. That's how many Earths could fit inside one of these red giants. But we're not even getting close to some of the biggest ones here yet. Let's go on to the red supergiants. Look in the far left there. That was the red giant we were just talking about, Aldebaran. These things are huge. Next to Aldebaran, you've got Rigel, the blue supergiant, and then we've got Betelgeuse and Antares, 2 red supergiants that are absolutely massive. And it's really quite fun to try and work out how big these things are, say, if the Earth was the size of a golf ball. So this is the Burj Khalifa. This is the largest building on the planet in Dubai in the United Arab Emirates. And it's quite large, like really, really high. You can see, compared to a lot of other skyscrapers, just how big this thing is. So imagine putting your golf ball at the base of the building. How far up do you think you'd have to go until you reached the equivalent size of Betelgeuse? Well, it'd be not equivalent to just 1 Burj Khalifa. It wouldn't be 2, nor is it 3, or even 4. In fact, Betelgeuse is the equivalent of 5 Burj Khalifas if the Earth was the size of a golf ball. 4 kilometers big. That's huge. And how many Earths could fit inside of a Betelgeuse? Well, imagine filling every single house in Sydney with golf balls. That's how many Earths could fit inside Betelgeuse. Huge. But we're not even at the biggest stars yet. There's another type of star called a red hypergiant, which is kind of like a close cousin to the supergiant. These are really, really large stars. And VV Cepheid here is one of the biggest stars that we know of. And how big do you think it is? Well, if you went to the Himalayas and you got a golf ball and you put it at the base of Mount Everest, then these red hypergiants would be the equivalent of the height of Mount Everest. 8 kilometers big. Huge, huge stars. And perhaps my favorite comparison, if the Earth was the size of a golf ball, how many Earths could fit inside one of these largest stars that we know of? Well, imagine covering the entirety of Australia, all of it, with a layer of golf balls. That's how many Earths you could fit inside this red hypergiant. So hopefully this kind of gets into your head just how big these stars are. They're huge, and even at like some of the biggest stars, the red hypergiant, some of my comparisons are breaking down because I don't know if you can properly imagine like filling Australia with golf balls or just how high Mount Everest is, but these things are really large. One second. So just another, again, if you have any questions, feel free to post them in the comments and I'll answer them at the end of the talk. So yeah, we've got these kind of red supergiants and their close hypergiant cousins, which are huge stars that are kind of nearing their end of their life. So once we get a star that's this big, we know that it's going to die soon. And when these stars die, something spectacular happens. The violent death of large stars. So normally these stars will go supernovae. So Georgie a couple days ago gave a talk on supernova. And what these are is essentially these stars have kind of grown so big that eventually they can't hold all their gas and dust together anymore. And so instead of just kind of letting it go, they explode in a huge, violent explosion. And they leave behind some spectacular kind of remnants. So here we've got a picture of the Crab Nebula. And if you were to go back about 2,000 years and look up where this thing is in the sky, you would just see a star, a particularly big red star, but a star nonetheless. In fact, about 1,000 years ago, Chinese astronomers observed this star exploding. They observed this supernovae, and it went really bright, that it was one of the brightest things in the sky. And so now, 1,000 years after that, we now can look up at the remnants of this star exploding and see this beautiful kind of pattern that, I don't know why it's called the Crab Nebula, but it kind of has a crab-like shape. I'm not sure. Now, we've actually got another star that's due to go supernova fairly soon, and it's actually the aforementioned Betelgeuse. So astronomers have been expecting for a while that Betelgeuse will eventually go boom, it will explode. But when I say relatively soon, astronomers soon isn't quite what we might say soon, so we're still talking within the next 10,000 years or so. So again, don't mark your calendars, you don't have to worry about letting the tea boil. It's going to be a while yet, but when it does explode, it will be bright enough to be seen during the daytime. It will be one of the brightest things in the sky. So that would be really cool when that does happen. What happens after the supernova though? What happens to that leftover bit of the star? Well, often it will turn into a neutron star. This is one of the densest things we know of. So there's a lot of stuff kind of packed into a really small space. You can kind of think of it as like a white dwarf on steroids. A very hot, very fast star here. And these, it's kind of amazing to try and think about just how dense these are. So imagine, I wouldn't advise it, but if you went out and went to one of these neutron stars, got out your teaspoon and you scooped up a teaspoon of the material, how much do you think that would weigh? Well, in fact, it would weigh about 900 pyramids of Giza. 900. Took a long time to kind of copy and paste these images here. That's huge. A huge amount of weight in one teaspoon. But how big is it? Well, you'd be able to fit it within the boundaries of Canberra. And I'm not talking about the scale as if the Earth was a golf ball. I mean, if you were able to lasso it and rope a neutron star and bring it to Earth, it would be able to fit quite comfortably within the boundaries of most of our cities. So these things aren't that big, but they're very dense and very energetic. In fact, these things spin so fast that they emit kind of really strong radio signals. So they emit strong waves, kind of like when you're in a car and you kind of tune into music or the news or something. Astronomers kind of picked up these kind of car signals, these radio waves from neutron stars. And I mean, we didn't know what these were originally, and we thought they could have been aliens trying to communicate with us. But as time went on, we found out that it was just because these things are spinning really fast and emitting these radio waves that we're getting these signals. So not aliens, instead neutron stars. But we've got one last stop in our journey. The biggest stars, the most massive, have a really special fate awaiting them. They're big enough that they won't collapse quite into a neutron star, but instead go all the way into what we call a black hole. So there've been a couple talks previously on black holes, so I won't go too deep into it. But here's kind of a little thought experiment that shows you just how weird these things are. So let's imagine that you decided to take a trip to a black hole with a friend, and your friend was kind of a bit adventurous and decided to go close to the black hole. What do you think you would see as your friend got closer to the black hole? Well, what would happen is your friend would slowly move towards it and get slower and slower and slower until eventually your friend reaches the edge of the black hole that we call the event horizon. And then they would freeze there. And that's all you would see. They would be frozen forever. You would never see them fall into the black hole, and they'd never be able to get out again. They would just remain there frozen in time for you to see. And that's one of the strange things about a black hole. Time essentially gets slower the closer you get until it stops at the event horizon. But that being said, your friend wouldn't actually be frozen there. You'd just be frozen from your perspective. Your friend actually would fall into the black hole and get stretched out in a process called spaghettification. So highly would advise don't go into a black hole. It's not a fun time. One of the other cool things, though, just quickly, that lately astronomers have done is most of the pictures of black holes you might see online are actually artist impressions. So they're kind of drawings that we kind of think what a black hole might look like the one on the right here. But on the left is a really special image because 2 years ago, we were able to get a lot of telescopes all working together to take a picture of an actual black hole. And that's what this picture of a black hole is. It was taken by the Event Horizon Telescope, which is a telescope that's essentially simulating a telescope the size of the Earth. Because you need a really big telescope to capture something so small on the sky. But it's really cool we managed to get a picture of a black hole. And hopefully within the next couple of years, we might even get another one from the black hole at the center of our galaxy. So that comes to the end of my talk. Just to kind of summarize what we've talked about, stars are really, really big and are really, really hot. They kind of start their life by gathering that gas and dust until they try and ignite themselves and turn on. And then when big stars die, they explode in a supernova and will turn either to a neutron star, which is really dense and spins really fast, or a black hole, which kind of is really kind of strange kind of phenomenon that we've discovered. And we don't know a lot about. Black holes are quite mysterious. So yeah, thanks for coming along. I'll answer some questions. If you've got any more, feel free to keep adding them in the Facebook comments. So I have a question here. Are stars really hot? Well, as hopefully you've seen, yes, they are. They're very, very hot. In fact, the surface of our sun is many thousands of degrees Celsius, like thousands of degrees. Not like on a summer's day here, it might be about like a really, really hot day might be in the 40s. We're talking in the thousands. And within the star at the core, we're talking millions of degrees. So really, really hot. If stars are bright, why can we look at them without hurting our eyes? It's because they're really far away. So when you've got something that's really, like, let's imagine that you're kind of standing on a highway and you've got a car coming towards you with its headlights on. When the car's coming towards you, the lights will get brighter. And that's not because he or she's kind of cranking up the brightness of the lights. It's because the car is moving towards you. And because it's getting closer, the light's getting brighter. Same thing with stars. Stars are so far away that despite them being really, really bright, you're able to kind of see them because the light has gotten faint enough that we can see them with our eyes. The sun is it's the same thing. The sun is so close, and that's why it's so bright, that we can't actually look at it with our eyes because it would burn them. Because it is a star that's close enough that it would hurt our eyes. Okay, I've got another question. Can cellular life be supported or live on the edge of the solar system? Good question. Unfortunately, for life as we know it, that is life like you or me, it would be very difficult to live at the edge of the solar system. It's just so cold there. So we're talking like single digits Kelvin, or like negative 200 degrees out there. It's just too cold for life as we know it to live there. However, we do think that there could be potentially life in some ocean moons of some planets. So there's a moon called Europa around Jupiter and a moon called Enceladus around Saturn. And these big ocean kind of icy moons, we think may have something like space fish potentially living in them. We just don't know, and there are a couple missions that are we're planning to potentially send out there to see maybe there are bacteria living in these icy moons. When the sun becomes a red giant, would the temperature of the Earth be a lot lower? Interesting question. Probably not. It would probably get a lot hotter because the sun, while its temperature would probably go down slightly, it would be a lot closer because it's expanded a lot. In fact, it wouldn't be just that Earth gets hotter, but we could even be gobbled up by the sun. So yes, the Earth would probably get quite a bit hotter when the sun becomes a red giant. But luckily, you or me will probably not be alive at that time. Do nebula change shape? Yes. So a nebula is essentially just a bunch of gas and dust all just floating about in space, and it's being moved by stars that are being formed or stars that are dying, explosions here and there. So nebulae change all the time. The reason that like we look up at the sky and like we might look at the Orion Nebula and see it in one shape pretty much all the time is because it's just so big and quite far away that things happen over such a long period of time in space that while it's changing and there's a lot of things going on, things are just so spread out that we can't see it really changing. If you were able to take a picture of the nebula for, I don't know, hundreds, thousands, millions of years, you'd be able to see it changing quite a lot. So yeah, nebulae do change shape quite a bit. Can stars attract their neighbors? Oh, that's a good question. So as you might have seen in the kind of little video I showed, some stars kind of move together. And that's what we call binary stars. So some stars are close enough that they won't kind of just be one star, but there'll be two kind of circling each other. And we see a lot of stars like this, a lot of binary stars. In fact, we've even seen some triple star systems where there's a lot of little stars all moving together. If you're more talking about whether two stars are going to collide or kind of crash into each other, that unfortunately is a lot rarer because stars, because things are so far away from each other, stars moving past each other will rarely kind of have a head-on collision, but instead might just move past each other. And then they might start a circle of a binary star. So two stars that are kind of going around each other. Next question. Does Saturn have a host star? Yes, it does. It's the sun. Just like us, it's another planet that goes around the sun, quite a bit further out, but it goes around the sun just like we do. And so, yeah, the host star of Saturn is the sun. If the sun doesn't swallow Earth when it becomes a red giant, would the white dwarf that eventuates produce enough heat to sustain life on Earth? That's a good question. I'm not sure of the answer to that, but my gut instinct would be no. Mainly because the star would be small enough and probably have lost a little bit of heat that it wouldn't be able to keep Earth at the temperature that it is now. That being said, I'm not 100% sure. That's a really good question, and yeah, so I'd advise you to kind of read up on white dwarfs and see just how hot and how big they are, and whether or not we actually might be able to keep the same temperature that Earth is now. My intuition would be that it would get a little bit colder. Can you please explain about the classifications of stars, like magnitude numbers and Greek alphabet stuff? Ooh, we're getting deep here. So astronomers tend to think about the brightness of stars in terms of magnitudes. That is, they give it a number. And magnitudes are kind of strange things because they're not just kind of saying if a star is a magnitude 2, it's twice as bright as, say, a star of magnitude 1. In fact, it's actually saying that it's 2.5 times fainter because it's on what's called a logarithmic scale. So when you've got a star that's 2.5 times brighter than another star, that would be then one step up the scale. So let's say you take a star that's magnitude 0, that's defined to be the star Vega in the night sky. Then a star that's 2.5 times brighter than that would be a -1 star, and a star that's 2.5 times fainter would be a 1 star. So that's how magnitudes work. Classifications of stars, that gets a bit trickier. So astronomers are kind of strange in that we classify stars based on how hot they are. And we give them a letter depending on how hot they are. So for instance, our sun, it's about 5,000 degrees, I believe, on its surface, and we classify it as a G-type star. Then as you get less hot, as you get cooler, you go from G stars to K stars, then M stars, and then you get into brown dwarfs. And if you go hotter, you become F, and then A, and then B, and then O. O's are the biggest blue supergiants. The letters are quite strange, you might think, but when you go back into the history of astronomy, they make a little more sense. It's due to the elements that were found in these stars. How far can you see back in time? Good question. So the furthest back we've been able to see is something called the cosmic microwave background. So this is basically the remnants of the Big Bang. That is when the universe kind of started. Kind of everything went bang at once. And we can use radio telescopes, that is these really big satellite dishes that you might see around, particularly Australia. We've got a lot of radio telescopes. We can use these to kind of study this kind of remnants of the Big Bang that's all around us. And this is it's roughly 13 to 14 billion years ago. So a huge amount of time in the past. Unfortunately, we can't see further back than that. And that's because any time before the cosmic microwave background, matter was kind of invisible. You can't actually see any light coming off of anything that was around before that. So the furthest back we can see is about 13 and 13.7 billion years ago, which is roughly the time we think that the Big Bang may have occurred. If a neutron star is so dense and small, does it produce any heat? Yes, very much so. These are very energetic stars. They produce a lot of energy, particularly in the ultraviolet and gamma rays. So not exactly light or heat as we know it. So like the sun gives off a lot of heat in kind of it gives off a lot of light and a lot of heat. But these stars kind of give off even more energetic kind of particles. So you know, if you go out in the sun, you might get a sunburn, and that's due to the ultraviolet rays of the sun. Neutron stars are like much, much worse than that. So imagine really, really, really bad sunburns, and that's what neutron stars will probably give you. Does the high density affect the orbits of the planets that might happen to orbit a neutron star? That's a very interesting question. So the interesting thing about orbits is that a planet will orbit exactly in the same way. It just depends on the mass of whatever it is at the center. So let's say you've got a really big star that's maybe, I don't know, 1 million kilograms. And then let's say you've got another neutron star, which is a lot smaller, but also 1 million kilograms. Then a planet going around both of those stars would see them exactly the same. It doesn't matter how that kind of matter is distributed. It could be like really, really compact like a neutron star, or it could be really, really big. The planet will go around just the same way. So no, it won't actually affect the orbits of any planets that might orbit it. It would be almost exactly the same as the star that was there before it. Finally, what's my favorite type of star? That's an interesting question. I'm quite a fan of the really big blue supergiants. I find them quite cool. Well, they're not actually cool, they're really hot, but just how kind of pretty they are. They're really big and blue and full of energy, and they have the most exciting lifetimes. Like, they explode, they turn into either a neutron star or a black hole, which is a lot more interesting than, say, just kind of petering out and just kind of losing their matter like a lot of other stars do. So yeah, I'd probably say like blue supergiants are my favorite. So yeah, that's about all the time we have for today, but thank you all for coming so much and listening to me ramble on about stars. I hope you've enjoyed it. And yeah, feel free to feel free to come along to any more of these talks we're doing. I believe we've got another one tomorrow evening. And yeah, stay tuned for any other events that Mount Stromlo Observatory will be putting on. But yeah, thanks all for coming, and I hope to see you around sometime.